Hey everyone, and welcome to this explainer. Today, we're going to be unlocking the secret language of electronics together, and we're going to keep it all in really easy to understand English. I mean, have you ever stopped to wonder how your exact voice travels through thin air to a friend's phone halfway across the globe? Or, how the data for this very explainer gets from the internet right to your screen? Well, it all comes down to signals, specifically the really fascinating relationship between analog and digital signals. We're going to explore exactly what they are, how they move, and why one of them has practically taken over the entire modern world. So, let's dive right in. All right, here's our quick roadmap for today. First, we'll do an introduction to signals, then understanding analog signals, followed by understanding digital signals. After that, we've got the great signal showdown, a look at real-world applications, and finally, a quick knowledge check to wrap things up.
Okay, let's kick things off with Section 1, Introduction to Signals, Carrying the Message.
At its absolute core, it really is just that simple. Signals carry information. That is literally their entire job. Think of a signal as a tiny, invisible messenger just sprinting from one place to another. Whether it's the rich, thumping sound of your favorite song blasting from a speaker, a text message buzzing in your pocket, or a massive computer file saving to your hard drive, all of that information is racing through circuits carried by a signal. In the world of electronics, this messenger usually takes the form of an electrical voltage or current that just surges and changes over time.
Moving right along to Section 2, Understanding Analog Signals, the Smooth Wave.
Let's break this down simply. An analog signal is continuous. It isn't chopped up into chunky pieces. So the crucial point is that word right there, smoothly. As time passes, the signal flows and changes without any sudden, jagged jumps at all. Because of this beautifully smooth flow, it can hold literally an infinite number of values within a specific range. It's not just on or off, it can be absolutely anything in between. Imagine sliding your finger up a smooth ramp. You don't skip over anything, right? You touch every single microscopic point along the way. That infinite, seamless transition, that's the pure essence of analog. You can really see how this waveform just continuously flows. Imagine this wave actively pulsing right now. The line glides fluidly up and down, a lot like gentle waves rolling on the ocean. There are no sudden breaks. There are no sharp 90-degree drops. It just continuously shifts, representing that infinite range of values we were just talking about. In fact, when you hear a sound out in the real world, like a dog barking or someone strumming a guitar, the actual sound waves traveling through the air around you look very much like this fluid, continuous motion. To really ground this, let's think about where analog signals live in everyday life. Honestly, your own voice is a perfect example. When you speak, you create a continuous, smooth, analog acoustic signal. An old-school glass thermometer? That's analog too. The red liquid doesn't just instantly teleport from 70 to 71 degrees. It smoothly expands and rises, hitting 70.1, 70.2, and so on. And if we look back at classic tech, things like vinyl records, cassette audio tapes, and VHS videotapes, well, they relied entirely on physically recording and playing back these continuous, flowing analog waveforms.
All right, Section 3, Understanding Digital Signals, the Stepped Blocks.
So if analog is a smooth ramp, you got to think of digital as a very rigid staircase. Digital signals are discrete, which is just a fancy way of saying they are broken up into distinct, separate steps. They're binary, meaning they operate entirely on just two values, 0 and 1. In easy English, when we're talking electronics, a 0 usually means there's no signal, or a super low electrical voltage. A 1 means the signal is fully present, or it's a high voltage. There is absolutely 0 in between. It is strictly on or off, yes or no, 1 or 0. It's an entirely different language from analog.
And this brilliantly illustrates that dramatic visual contrast. Instead of those smooth, rolling ocean waves, we have rigid, blocky steps. Imagine these hard blocks pulsing down a wire. The signal instantly jumps from 0 down at the bottom, straight up to 1 at the top. It holds steady for a moment, then instantly drops right back down to 0, no sloping curve whatsoever. This stepped, discrete, highly organized movement is the literal heartbeat of all modern computing. Because our computers operate using these exact discrete steps, the files we interact with every single day are built entirely on digital signals. That MP3 song you're streaming? Digital. The JPEG photos you just snapped on your phone? Digital. The MP4 video file you might be watching right now, plus all the background processing inside your laptop, it is all constructed from billions of those little 0 and 1 blocks just flashing back and forth at lightning speed to create the media we consume. Okay, here's where it gets really interesting.
Section 4. The Great Signal Showdown. Analog versus digital. When we actually compare these two, noise and storage are the major battlegrounds. In electronics, noise just means unwanted interference. Because analog signals are delicate and smooth, they get easily messed up by this noise. It's kind of like trying to perfectly trace a beautiful painting while someone keeps bumping your elbow. Digital signals, however, they're tough. Because they're just rigid ones and zeros, they're highly resistant to noise. The computer knows exactly what a 1 should look like, even if there's a little static. And storage? Well, if you copy an analog cassette tape, the copy always sounds a bit worse. It's like a game of telephone. The message degrades. But digital? You can copy an MP3 file 10 million times, and that 10 millionth copy will sound mathematically perfect. Literally zero quality loss. This massive advantage continues when we need to send messages over huge distances. If you send a smooth analog signal down miles and miles of cable, that delicate wave slowly gets weaker, it absorbs background interference, and it distorts. It just arrives fuzzy. But if you send a digital signal, those sharp, discrete pulses of ones and zeros, it acts almost like a super resilient Morse code. It travels incredibly long distances with almost zero degradation. The receiving computer just reads the rigid pulses, and the message stays perfectly clear. And what about the heavy lifting inside our actual devices? Well, processing delicate analog signals requires complex, highly specific circuitry. And honestly, it's pretty difficult to upgrade or scale up an analog system. Digital processing, on the other hand, is basically a computer engineer's dream. It's mathematically straightforward, it's incredibly fast, and it is easily scalable. If you want a digital computer to do more work, you just add more microchips to process those ones and zeros faster. It's a highly efficient and totally predictable system. Section 5. Real-world applications. The big question, which is actually better? The honest truth, they both have very specific, totally vital jobs. Analog is actually way better for capturing real-world, continuous data in its purest, rawest form. If you want to capture the true, uncompressed, emotional nuance of a live symphony orchestra, an analog wave is the most natural way to record that. However, digital is vastly superior for manipulation, for storing data infinitely without losing quality, and for fighting off that pesky noise. We live in a fast-paced information age that requires perfect, rapid data storage and transmission. And that is exactly why digital has claimed the absolute throne as the global standard for our modern devices. All right, let's wrap things up with Section 6, a quick knowledge check. Let's see how much you've absorbed today. Here's our first question. Think back to our big showdown. Which type of signal degrades, gets fuzzy, or loses quality when it has to travel over really long distances? And the answer is analog signals. Yep, because they rely on that continuous, delicate flowing wave. Any interference over a long distance permanently alters and degrades the actual shape of that wave. Awesome job if you remember that one. Okay, let's try one more. Why are digital signals overwhelmingly more suitable for our modern computers? Think about those sharp ones and zeros and what exactly makes them so robust.
The biggest reason? They are far more resistant to noise. Computers absolutely need mathematical certainty to process data. The discrete, binary nature of digital signals means that a slight bit of electrical background noise just won't accidentally flip a 0 into a 1. It keeps your data perfectly intact.
You guys have done a truly fantastic job navigating the secret language of electronics with me today. But before we go, I want to leave you with one final provocative puzzle to think about. So, we learned that human speech is a continuous analog signal, right? But the smartphone in your pocket is entirely digital. So, when you make a phone call, how exactly does your digital phone take your incredibly complex, flowing analog voice, slice it up into rigid blocks of ones and zeros, blast it into space, and turn it back into an analog sound wave that your friend can hear, all instantly without losing the emotion in your voice? It is a fascinating marvel of modern engineering, and I highly encourage you to keep exploring how this incredible conversion happens all around us every single day. Thanks so much for joining me on this explainer, and keep learning.